Your processor is faster than the benchmark says, but the benchmark your phone uses might be measuring something that doesn't exist in real life. That gap, right there between those two lines, shapes billions of dollars in hardware purchasing decisions every year. Hardware vendors optimize for it, compilers are tuned to it, and the scores you read in reviews are shaped by it, whether the reviewer knows it or not. This is tech. And this is what benchmark scores actually measure, and what they quietly leave out. To understand where benchmarks go wrong, you have to start with why they exist. Before standardized benchmarks, buying a server was like buying a car based on the manufacturer's own brochure. Every vendor measured differently. Every comparison was apples to oranges. Benchmarks solved that problem by giving the industry a shared language, controlled, repeatable, comparable. That's not a small thing. When a hospital buys 100 servers or a bank chooses a database platform, they need a number they can compare across vendors, across time, across procurement cycles. Benchmarks gave them that number. But benchmark design faces a fundamental tension that no benchmark has ever fully resolved. The more controlled and repeatable a test is, the easier it becomes to optimize specifically for that test, and the harder it becomes to predict what the hardware will do in the messy, varied conditions of actual production. This trade-off is inherent. It's not a design flaw. It's a design constraint that every benchmark consortium has wrestled with since the beginning. No benchmark perfectly captures all production scenarios, and none ever will. And here's the dimension that makes this trade-off especially difficult to communicate in a single number. Different workload types, burst versus sustained, single-threaded versus multi-threaded, I/O-bound versus compute-bound, often show dramatically different performance characteristics on the exact same hardware. A chip that dominates a 5-second burst test may look very ordinary under a 60-second sustained workload. A processor that excels at single-threaded tasks may struggle when every core is loaded simultaneously. And an I/O-bound database query hits completely different bottlenecks than a compute-bound video encode. This is why a single benchmark score cannot tell you how fast your device will feel. Not because the benchmark is dishonest, because the question it's answering is narrower than the question you're asking. The question is, what happens when the number starts optimizing for itself? The SPEC CPU benchmark suite was first released in 1989. It was designed to measure how well a processor and compiler handle a set of standardized workloads: integer math, floating point calculations, memory access patterns. For decades, it shaped which chips got bought, which architectures got funded, and which compiler teams got credit. And then something interesting started happening. Compiler vendors, the teams who write the software that translates code into machine instructions, discovered something useful. The SPEC benchmarks used fixed workload file names, and a compiler that recognized those file names could apply optimizations specifically tuned for those workloads, not for your spreadsheet, not for your video encoder, just for the benchmark. SPEC's run rules explicitly prohibit optimizations triggered by workload file names. That clause is right there in the documentation, publicly available at spec.org. The consortium recognized this problem and built rules specifically designed to stop it. The run rules are dense, detailed, and clearly written by people who understood the incentives they were trying to constrain. But detection and enforcement remain imperfect, and the run rules themselves acknowledge that ambiguity. The boundary between a general-purpose optimization and a benchmark-specific one is genuinely difficult to police, even with good faith effort on all sides. Researchers examining compiler behavior have estimated that benchmark-specific optimizations may inflate scores by roughly 10 to 15% on certain subtests. That estimate is contested. The magnitude varies by workload, by compiler, and by how strictly you define benchmark-specific. Compiler teams dispute whether their optimizations cross the line the run rules draw, but the mechanism itself is documented and real. A compiler can make a benchmark 10% faster without making your applications faster at all. And the run rules, however carefully written, cannot perfectly close that gap. This isn't a story about fraud. SPEC designed its rules to prevent exactly this. It's a story about what happens when a measurement tool becomes the goal, and how hard it is to write rules tight enough to stop that drift, even when everyone agrees the drift is a problem. Every benchmark faces this tension between controlled repeatability and real-world representativeness. SPEC understood it from the beginning. Their run rules exist precisely because the consortium recognized the problem. But no set of rules can perfectly close the gap between what a benchmark measures and what it's supposed to predict, especially when the incentives to find that gap are worth hundreds of millions of dollars in procurement contracts. In November 2020, Apple released the M1 chip. The Geekbench 5 single-core score came in at approximately 1,750. The headlines wrote themselves. And the headlines weren't wrong, exactly. In that specific test, a single-threaded burst lasting 5 to 8 seconds, the M1 genuinely achieved those numbers. But Geekbench 5's single-core test runs for less than 10 seconds. Real workloads don't stop at 10 seconds. And here's where workload type matters enormously, in ways that a single benchmark score cannot show. A burst workload and a sustained workload behave differently on the same hardware. A single-threaded task and a multi-threaded one hit different bottlenecks. An I/O-bound database query and a compute-bound video encode stress entirely different parts of the chip. These distinctions are not edge cases. They are the normal range of what real software actually does. Video encoding runs for minutes. Compilation jobs run for longer. Scientific computing can run for hours. In sustained multi-threaded workloads, the M1's advantage over comparable Intel processors was real, but it was 20 to 40% smaller than the burst benchmark suggested, depending on the workload type. Thermal throttling and memory bandwidth constraints, neither of which appear in a short burst test, were the limiting factors. This isn't a flaw in the M1. The chip is genuinely impressive silicon. Apple's engineers made real architectural choices: unified memory, high bandwidth interconnects, aggressive power efficiency, that produced real advantages in the right workloads. But a benchmark that measures 5 seconds of burst performance is not measuring what most users do most of the time, and it isn't designed to. The score was accurate, the context was missing. And the gap between those two things is where the misleading happened. The same tension appears in AI hardware benchmarking, but the numbers are larger and the stakes are higher. The MLPerf consortium was founded in 2018 to bring standardized measurement to machine learning hardware. The goal was the same as SPEC's: give buyers a common language for comparing AI accelerators across vendors and generations. And MLPerf did something important that earlier benchmarks didn't always manage. It required vendors to disclose their submission configurations. Batch size, precision mode, hardware configuration. All of it on the record in every submission. That transparency matters. The consortium built disclosure into the rules specifically so that buyers could evaluate what conditions produced the headline number. The information is there. It's public. It's required. But transparency only helps if buyers know where to look, and most procurement conversations never get that far. Here's what the disclosed configurations actually show. Those numbers are real. They reflect what that hardware can do under those specific conditions. But int4 precision, 4-bit integer arithmetic, is not what most production AI systems use. Most deployed inference systems run at FP32 or at minimum FP16 because accuracy matters in production. A financial fraud detection model running at 4-bit precision may produce meaningfully different results than the same model at 32-bit precision. When you run the same hardware at the batch sizes and precision modes that production deployments actually use, the documented discrepancy between submission performance and deployable performance ranges from roughly 3 to 8 times. The MLPerf documentation requires vendors to disclose exactly these configuration details. The information is there. But a headline that reads 6,800 inferences per second and a deployment that delivers 890 are describing the same hardware under very different conditions. And most purchasing conversations never make that distinction explicit. This is the same trade-off we saw with SPEC and with the M1. The benchmark is doing what it's designed to do. The gap opens in the space between the controlled test and the messy production environment. And it opens differently depending on which workload type you're running. Some benchmark gaps aren't about burst versus sustained, or submission configuration versus production configuration. They're about time itself. TPCC has been the dominant database transaction benchmark since 1992. It was designed to model a warehouse inventory system, order picking, stock-level queries, batch updates. 5 transaction types, all modeled on how a single warehouse location processed orders in the early 90s. For its original purpose, that was an accurate model. 1992 warehouse transaction processing really did look like that. Sequential access patterns, predictable concurrency, modest data volumes. TPCC was not a bad benchmark. It was exactly what it needed to be, for the world it was designed to measure. But modern online transaction processing looks nothing like a 1992 warehouse. The access patterns are different. Sequential warehouse picks versus random customer queries scattered across millions of records. The concurrency models are different. A single warehouse location versus distributed multi-region systems handling thousands of simultaneous transactions. The data volumes are different by orders of magnitude. Database researcher Michael Stonebreaker and colleagues published analysis in 2011 showing that the correlation between TPCC scores and performance on modern e-commerce and financial transaction workloads was poor. A correlation coefficient below 0.4. That finding is worth treating carefully. It's reported academic research, not settled consensus, and the precise figure has been debated. But the directional conclusion is broadly accepted. A benchmark designed for one world has limited predictive value in a very different one. And the world of database workloads changed faster than the benchmark did. One more complication worth naming. In January 2018, the Spectre and Meltdown security patches were released for Intel x86 systems. On I/O-heavy workloads, those patches reduced benchmark performance by 5 to 30%, with the exact impact varying significantly by workload type and system configuration. Any historical benchmark comparison that uses pre-patch figures without labeling them is comparing different systems, even if the hardware is identical. The patch date matters. the workload type matters. Neither shows up in the headline number. So here's what I think is actually happening across all of these cases. Benchmarks aren't broken. They aren't fraudulent. They do exactly what they're designed to do. Measure specific scenarios under controlled, repeatable conditions. That controlled repeatability is genuinely valuable. Without it, procurement decisions would be even more chaotic than they already are. The problem is that a number designed for controlled comparison gets treated as a prediction of all real-world experience. And different workload types show dramatically different results on the same hardware. Burst versus sustained. Single-threaded versus multi-threaded. I/O-bound versus compute-bound. A chip that dominates one of those dimensions can look very ordinary in another. And no single score can capture all of those dimensions at once. That's not a flaw. It's a fundamental constraint of what a number can represent. The benchmark isn't lying to you. It's answering a narrower question than you think you're asking. Once you see that distinction, you start reading benchmarks differently. You ask what workload type was tested, whether it was burst or sustained, whether the figures are single-threaded or multi-threaded, what precision mode the AI submission used, whether the comparison crosses the January 2018 patch boundary, and you stop treating one number as a verdict. These scores remind us that every measurement is a choice, and the choice of what to measure shapes what you see. But benchmarks aren't the only place where the gap between a controlled test and messy reality quietly widens. I'm here to help you know the signals from the noise. What benchmark have you seen misused? In a review, a purchase decision, or a job interview? Tell me in the comments. See you at the next test bench.